Okay, so we have treated the problem of non-inertial frames of reference in terms of two frames. If the second reference frame is moving with respect to the other one and has a rectilinear motion as well as a rotation, then what is the relationship between the velocities and the acceleration? We've derived that. As I said, this expression do not try to remember, but it comes from dynamics. But this is a useful equation. If you require this in an exam setting, I will actually give it to you. Now, what I have done here is I have revisited this particular problem, and here we had this cart. If you remember, we had done this problem some time ago, and we had this cart where this jet is coming in and is going out through this path, and the areas of this cross section and this cross section are the same, and here the jet is being deflected with theta. The earlier question had been that what happens if what are the forces required to keep the v card is equal to 0, or basically what are the forces required to keep the card stationary. But now let's say this term is not equal to 0, and that you have measured this v card, v jet and all, and if you can create a relationship between all the different terms, so then we have to so now what you will have to do is you have to create again you will use the same control volume as before, which is attached to this to the cart itself, and now the control volume is going to move with the cart. So the control volume is also going to have a velocity of v cart, which is a non-zero velocity. Now, all along the equations that we have been discussing till now, there have been equations for control volume that is not deforming but not also in acceleration with regards to an inertial reference frame. But here now this v dot, the time derivative of v cart is also not known to you, because we have not provided you what v cart is. So in that case, what is the question would be that what are the relationships between all these different quantities that are there present in this particular problem. So if the control volume also is moving, then you have to account for that extra fictitious force that comes in because the control volume itself is moving with the cart, and that's exactly what we have done. So I have written here the modified equation for this control for the conservation of linear momentum with respect to this new axis, which is y small x. These are the new axis with respect to which you'd look at the control volume, and then the control volume would be stationary. So then you have to just change the right hand side to account for the acceleration, and then okay, the other interesting thing is that in this case we had all these different terms of for rotation, to account for rotation. Here you don't have that, you just have a rectilinear acceleration. Okay, so all the other terms just drop out, and you only have the linear acceleration term. And then when you solve for this for a steady state condition, just like before, we end up with this relationship which relate acceleration, v jet, v cart, and all the other parameters. Okay, and this was the question asked. So you can go through it at your leisure. Again, I'm not going to solve it for you right now, because we have to also move on to some other topics. Okay, so till now what have we been doing? We have been looking at finite control volumes. When you have finite control volumes, you have to create an integral equation to relate the happenings within the control volume plus the mass fluxes to some of the other terms which are important in that setting. But now we have to ask, is there a differential equivalent of all these equations that we have been seeing? So is there so we had started out with the conservation of mass, right? Okay, so what we want to do now is differential approach. So now your control volume is still there, but now your control volume is no longer, so we still have a control volume, but now the size of this is dx, and this is dz, and this is, let's say, dy. So basically we have taken our finite control volume and then we have gone on to shrink it. Of course, we are looking at the problem in the limit that dx, dy, dz, they all tend to 0, right? So you had, so if you have a finite control volume, you end up with integral equations. But when you are going to look at differential control volumes, what do you expect to get? You expect to get a partial differential equation governing that system. So let us do the problem of the mass, conservation of mass for, sorry, not of, for a differential control volume. Okay. Now there are two ways of doing it. One, the first step one is the sorry, not step one, method one. The first method is to not worry about all the integral equations that we had seen, but just think of how to write how to do our balance for a differential control volume. So let's look at a differential element. Okay, and let's just consider right now the dx part. We'll quickly be able to figure out expand it into the 3 dimensions. So let's say the mass flux at the center is m dot x. Okay, so let us say that rho, u, etc. are given. So you know the density at the center is rho, and the velocity at the center is u bar, and m dot x is the flux through the center. Then the question is, what is my m dot x? So what are the fluxes in my particular problem? Wait a second, let me just, okay, so I want to see, so there is some flux coming in from the left hand side, and there will be some flux also going from the right hand side, right? So my m dot through the left, okay, and right now, as I said, we'll just think of it as a one dimensional problem, is just m dot x plus del mx by dx by Taylor series expansion, right? You have already seen this kind of a arithmetic before, calculus before. And what is happening on the right? M dot right is also rather straightforward, which is just m dot x. Here you had a negative sign, and is the same thing but with a plus, right? So let us just expand this a little bit more. So m dot x is basically nothing but rho ux dy dz, right, plus del x of this same quantity plus multiplied by dx by 2. Sorry, I've just sort of run out of space here. Maybe I should just put it here, dx by 2. Okay. So what do you get? You have del x of rho ux, and then I'm just going to take all this dx, dy, dz out, right? So what is the net mass flow rate into the control volume? Net mass flow rate into the CV. That m dot net will be equal to minus, okay, sorry, there is a by 2 here, yeah, del x of rho ux dx dy dz, right? But this was just considering the one dimensional case. So if you take all the 3 dimensions, then it's not very difficult to see that what you will have is simply this. Del z of rho uz dx dy dz, right? So this is the entire net mass flow rate. Good. So this falls into a very nice form. Now the rate at which mass is increasing in the control volume, or dm by dt del t inside the CV, is simply del time of rho dx dy dz. This term inside, this is the total mass inside a differential control volume, right? And rho again as the density at the center of the control volume, right? So now what does my principle of conservation of mass say? The principle of conservation of mass says that the rate of increase of mass within the control volume must be equal to the net rate at which the mass enters the control volume, right? So my del m by del t, because mass cannot be created, this increase must be accounted for by this particular quantity. Okay. So, by the way, right now we are not going to the Reynolds transport theorem method. We are just considering, we are just taking a differential control volume and just applying our understanding of what the conservation of mass says. So conservation of mass says that if there is any increase inside the control volume, that has to be accounted for through fluxes through the side. So this quantity is now going to be equal to my m dot net, which we have written here, right? So this, what do we get? This is del t of rho, of course you have the dx dy dz, right? So that, and we will have that on the other side as well, right? So this quantity is rho ux plus del y of rho uy plus del z of rho uz. Sorry, this is not the right bracket. The right bracket is this, into of course again dx dy dz as we had gotten, right? So this, rearranging these terms, it's rather straightforward to see that the equation is del rho by del t. Oh, I have made a mistake, haven't I? This is supposed to be t, not x. del t plus del x of rho ux plus del y of rho uy plus del z of rho uz equal to 0. Great. So this is also, so this, by the way, is the equation we are looking for in component terms, right? This is the continuity equation, and then this also can be written as so the same equation, if you want to write it in vector form, you will write it as del rho by del t plus this dotted with the u vector equal to 0. Sorry, rho u vector, not u vector. This is rho u equal to 0. Or in index notation, if you want to write it, this equation is rather straightforward, so it's not a bad time to just, if you want to check your index notation or practice it, this is probably a good time, right? So these are the important equations. They're all equivalent. They're all the same equation, right? So oh man, okay. So this equation, this form, which is the component form or the vector form or the index notation form, they are all the same and they are the continuity equation. They are also called the continuity equation in fluid mechanics, and they are basically a statement of conservation of mass for our system. Okay, great. So I had said before we had just that this is the method 1. So we should look at method 2. And what was the control, the equation of conservation of mass for the control volume? Okay, so just recall that equation we have seen already. Sorry, this is already ddt of the control volume term rho dV plus the control surface term, which is going to be simply this, and this is equal to 0, right? This is what we have seen for a finite control volume. Okay, so now consider, okay, I'll just move to the next page, then I'm just going to run out of space here. Okay, so now consider a fixed control volume, so that ddt of the CV term, this is the same as, if the control volume is fixed, it doesn't matter whether the ddt is inside or outside, right? So these two are equivalent. So this is del rho by del t dV, and this urel is just the u, right? So the control volume is fixed. It's non-deforming and not moving with respect to the fluid. Now I hope you remember the Gauss's divergence, the Gauss's theorem, also called the divergence theorem. We had seen it few classes ago. I can't really remember which class right now, but we have seen this. I think this is in okay, yeah. So it is in lecture 4, part 2 of 2. Towards the end of that lecture, we have discussed the Gauss's theorem, also called the divergence theorem. So recall that from Gauss's theorem. Now see, why are we invoking a Gauss's theorem? Is here one is a control volume term, one is a control surface term, right? It would be nice if we could just mix these two together. If this also was a control volume term, we could bring all these different quantities under one integral, right? So that's what we are trying to do. We are trying to put this ddt inside. We've already done one part of the job. One is a control volume term now fully. And now if I can also make this a control volume term. So from Gauss's theorem, if you just care to look back at the notes of that particular class, then you will see that, okay, I can drop the rel now, and that this is going to be equal to the integral over the control volume for this term. Okay, where, by the way, this is in general a triple integral, this is a double integral, right? So we have related them, and now so now if I use this version for my first term and this version for my second term, I can recreate this particular equation, and what I will get is one single integral which is over the control volume, and now I will have del rho by del t plus this divergence term dv is equal to 0, right? But this is for an arbitrary control volume, right? I have not specified what this control volume is, but this statement terms seems to be true. So if this is equal to 0 for an arbitrary control volume, then it has to be 0 always, and only then can this integral be 0. Okay, but this is, since this is for an arbitrary CV, it can be true if and only if IFF is if and only if del rho by del t plus okay, great, we have gotten back the same result. So we have worked out the same result through two different methods. So method 2 used the control volume formulation that we had already used, the integral control volume formulation that we have already seen, whereas method 1 just used our normal, bookkeeping for a differential control volume, and we are able to get the same answer. Fantastic. So this is now the continuity equation, but you have to remember this there's a star sign that I should put, that this is without a source term. Okay, so this is without generation of mass within the CV itself. Okay, so this is without a source term, and if you have a source term, then you have to add that together, because remember when we were arguing that the rate at which the mass is increasing has to be equal to the mass that is coming in, okay, through the sides. It is not accounting for the fact that there might be mass generation within the control volume itself due to some activity, okay, which is generally true. I mean, there are not many situations where mass can be generated. Okay, good. So let us study this equation a little bit more. Okay, so let's look at the notes for this equation. Now, for a fluid where the density is constant, density remains uniform and constant, this simplifies to so if the density is uniform and constant, then what happens? This first term goes to 0 because this is uniform and constant. So it is not varying in space, neither is it varying in time. So this term goes, and this row can be just taken out, and you end up with this being the continuity equation for constant density fluid. Okay, but remember that this comes because you have the density is uniform and constant. Okay, so the two were required. Now, another very important type of fluid that we keep on encountering is what is called the incompressible fluid. Incompressible fluid. What is this thing? What is such a fluid? Well, an incompressible fluid is one in which the density of a particular piece of fluid packet remains constant. That's the definition of an incompressible fluid, which means in mathematical terms this quantity has to be 0 because we are following a fluid packet. Okay, so this is the definition of an incompressible fluid. Okay, so the fact that it is incompressible does not necessarily mean that the density is same everywhere in the flow. You can have two different sections of the flow such that, so you can have a section such that you have flows in different streamlines, and let's say this is an ocean, and you can have density increase as you go through the different layers, but in each fluid layer, the fluid is straddling and is going along a path such that its density remains constant. So that is the definition of an incompressible flow. So sometimes people confuse incompressible flow with this particular definition, that the density has to remain uniform and constant. That's not true. So you can have a situation where the flow is incompressible, but there is a density gradient in the fluid itself. Okay, and ocean is a fantastic example because there's something called a stratified flow in the ocean, where the density of various layers of ocean water, it varies due to many factors, which could be salinity, for example, it could be temperature. Okay, and it could also be just the weight of the layers ahead of it. So all that combined. Okay. So now let us just look at what our equation for the incompressible flow will look like, the continuity equation for that. So we have that d rho by dt is equal to 0, which means that del rho by del t plus u dot this term is equal to 0, right? Now continuity, which is a separate equation, that equation is del rho by del t plus del dot rho equal to 0, right? Now what I can do is, I have two places I have del rho by del t, so I can just substitute this del rho by del t with this part, right? So if I do this substitution, I will get minus this equal to 0. Okay, so now if I expand this, so I have these two variables for which there is a derivative operator. So what I can do is, I can just use chain rule, and if I do that, then I will have two terms for it, and this is equal to 0 now, right? Now you can see, wait a second, you can see that these two terms are going to cancel, right? So you are going to get what? You are going to end up getting this is equal to 0. So interestingly, we started off by claiming that this is the definition of an incompressible flow, but when you apply that to the continuity equation, you end up getting this as the continuity equation for an incompressible flow, which is the same as the continuity equation in case of a flow where density remains uniform and constant. So I think there is a good reason why people are often confused and often take this as the definition of the compressible flow itself. So although it's not correct to say that this is the definition of incompressible flow, but you can probably see where this confusion comes from. Okay. So what I'm going to do is, I'm going to give you a problem statement, okay, and what you have to do is, you have to solve this problem, and I will work it out in the next class. So I will not work it out today, but I will work it out for you in the next class. And the situation is the following. So we have a piston, this, and okay, that looks like a piston. Good. Let me choose another color. So let's say this is moving with a velocity v, and here there is a gas with density rho. Of course, this density is now changing with time, right? And let's say that this length here is L. This is again a function of time. This is the length. Okay. So the piston compresses the gas. So we have a piston. So your question is, okay, piston moves at constant speed v. Let's say this v, which is given to you, and the gas density and A is the initial length, initial density and length are rho naught and L naught. Okay, and assume that the gas velocity varies linearly from this face where it is going to be v, but here it is going to be 0, right? So because at this end of the wall the gas cannot move. So the gas here has to move. So the gas adjacent to the piston has to move at a velocity v, of course, but the gas molecules at the wall don't have to move at all. So there is going to be a velocity profile inside the gas itself. So the question for you is, if the gas density varies only with time, determine determine rho t. Okay, so you guys give it a shot and I will work this problem out in the next class. Okay, so now there is something. So we have started looking at the differential equations, and these differential equations have their own importance in the scheme of things. And of course, now that you have seen before the different equations of the conservation for linear momentum, conservation for angular momentum, conservation of energy, there will be the equivalents of that for the differential control volume. We will look into those, but this is the time when we are changing our viewpoint from from integral to differential, right? And there are some things that I had left out of, which were in chapter 2 of the book, but then I had chapter 3 of the book, but I had sort of postponed it for later. And the reason I had postponed it because I wanted to wait for the differential discussion to come up to introduce that. And then there are these stress tensor and the deformation tensor. Okay, the velocity gradient tensor rather. So let us discuss fluid element deformations. In the next class we will discuss, depending on how fast we go, I think we will also introduce ourselves to the stress tensor. Okay, because we are going to need to understand the tensors and their relationships to all these conservation equations very, very soon. So to understand fluid element deformations, the first thing we have to know that any general deformation, it can be composed into a set of sub deformations. Okay, so let's say any general deformation can be broken up into, can be seen as a combination of one is translation, two is dilation, some people also call it dilatation. Okay, so you will find this word also quite a lot, dilatation, 2 This is rotation. Yeah, the two words look quite similar. The other is rigid body rotation. And the final is angular deformation. So what it means is that if you have, let's say, a square at the beginning of the game, and the square has now deformed in some way. So, oh, sorry, this is not a good deformation. Wait a second. Okay, so the square has deformed. Okay, so this is general deformation. Then this deformation can be seen as a combination of either translation, where you had the initial square somewhere and now it has moved to another location. Okay. Wait a second. Let me do this. Let me color code this. It will make our lives easier. Okay. Okay. So it will be easier this way. So this general deformation can be seen as a combination of just rigid body translation, which means that this is the general deformation. Sorry, this is a general deformation. This is a translation plus a dilation. Dilation is, the meaning of that is exactly what it sounds like, that you had an initial square, let's say, and then it has either grown or either shrunk. So it has just scaled. So the dilation is basically a scaling in size. Okay, so this is dilation. Or angular deformation, where you had a square and the angles of these parallel lines, they have been deformed. This, or the final one, is and the final one is simply rigid body rotation. Just like, okay, I am running out of space here. Okay, let me, so this is dilation. Oh my, this is dilation. This is angular deformation. Plus there is one more, and that is, okay, just a second, I have to use this. Okay, this is a pretty bad drawing, but what I wanted to do was to say, take the same square and now I have rotated it. That's it. Okay, so this is signifying rigid body rotation. And this is quite remarkable that you can break up any general deformation into these four deformations, which are include translation, dilation, angular deformation, and rigid body rotation. And we'll study each of these one by one, okay, and we'll see how this relates to the deformation of a fluid element. So essentially we want to talk of differential volumes, and these are at the small scale. So this box is being shrunk down to dx size, and we want to look at how a fluid particle which is very small, which is a differential element, can be deformed in in different ways. Okay, so we will continue from here in the next class. So I'll just stop here.